Hi everyone. In this video, we'll develop an automatic speech recognition pipeline in Python from scratch. And what I'm hoping to achieve is introducing some concepts in this field at a high level. And I really wanted to make this video for a while because there's surprising lack of beginner-friendly material in this field. So you might be familiar with voice assistants like Siri or Alexa, and these are providing clear responses to human requests in the form of speech. You're listening to the TV or watching YouTube, maybe you turn on closed captioning. All of these things are using sort of speech recognition under the hood, and this is essentially a computer model which is translating our human speech into text. It started here. You really don't have to worry about any familiarity with machine learning or just a general, if you've written a few lines of Python, that might help. But everything we're going to talk about today will be in this Google Colab. So Google Colab is a service provided that you don't really have to set up any Python environments. Everything's handled for you. All you need is access to internet and you should be able to run everything there. Make sure that you're connected to a GPU runtime because this will help with training your models. To train a speech recognition model, the first thing you're going to need is speech data. Working with Amharic. Amharic is one of the official languages of Ethiopia, and I wanted to choose a low resource language, especially since there isn't too much going into this area. There's a lot of English, a lot of Mandarin or Spanish speech recognition models, but there's not too much in this community. So if we go to this GitHub repository, we'll see that it is about 20 hours of training data and 2 hours of testing data, and they're all segmented into about 3 to 10-second clips. So we look here in the data, or let's look at the testing data. There's this wave file, and these are all the raw sound recordings. And if we go to text, we see that there is the name of the sound recording file and the transcription of that file. So the first thing we're going to need to do is we need to identify what is the name of the path to the wave file and the associated transcription. So this script here is going to take care of that. So if we run this, and then what you need is this train trans CSV. So I attached that file to the description, but essentially what you're going to do is you're just going to copy this and this into your Colab space. You've uploaded the files into your Google Colab space. What you're going to do is copy the path of these files, and we're going to define these as follows. We're going to create a data frame that takes this path of the CSV. So let's look at the CSV very shortly. What it does is just segment the name of the WAV file and the transcripts into a CSV file. So it takes that into the data frame and it names one of the columns transcript and the other one name. To this data frame, we want to append a separate column which takes the name and adds the .wav and also takes in the root of the file. So if we run this, we'll see that we get this nice data frame. It has a transcript and the path of the WAV file. Let's see what this data looks like. We're going to take a random integer from 0 to how many samples we have in the training data. And we're just going to load that using something called Librosa. Librosa is this Python package for audio analysis, and it takes care of some of the high-level stuff that we're going to do with pre-processing this data. So first we're going to load that using this Librosa, and we're just going to look at what does the waveform look like. Once that's run, you'll get something like this. We see that we have a transcription here. This is the transcription associated with the wave file. And then we have this waveform here. Remember that speech is essentially amplitudes of your vocal cords over time. So on this y-axis, we have amplitude, and on this x-axis, we have time. So your amplitude of the audio signal is changing over time. And let's see what does this speech sound like. So if we run this file, run this this cell where you get this.
የተለቀቁት ምርኮኞች በአካባቢያቸው ሰላማዊ ኑሮ እንዲኖሩ የትራንስፖርትና መጓጓዣ ገንዘብ ተሰጥቷቸው መሸኘት
Okay, so I ran this file. Hopefully you've been able to hear it. Problems with this signal is that you see there's a lot of silent regions here, So you'll see that it's relatively flat here. This is all background noise. And we want to minimize that as much as possible and focus on whenever the speaker is actually speaking. So we're use something called z-score normalization. And essentially all it does is it's this formula here. You're taking the value of the data point and subtracting the mean and dividing by the standard deviation. And it is transforming the data such that the mean is 0 and has a standard deviation of 1. Background noise will essentially go to 0. So if we run this, which essentially just does that computation we described, you see that the background noise effectively goes to 0. And we've enhanced the parts of the audio signal where the speaker is actually producing sound. The other thing is that it would be nice if we could just start the signal when the speaker starts talking. So what we have to do is something called trimming. So we're trim the signal at these areas, or cleave it, and Librosa takes care of this for us with this trim function. So you just pass the audio samples, and this top dB stands for the threshold. Let's say that this is about 15 decibels. We want to ignore everything that's less than 15 decibels and keep everything that's above that. And we're classified that as our intended audio signal. So we run this, we'll get our trim signal. So if we compare it to this normalized signal, it starts wherever the speaker begins to talk. Last thing we want to do before we're sending it to our model is resampling it. So right now, it's sampling the audio signal 16,000 times a second. So sampling rate, 16,000 hertz. And we want to make it half of that to reduce our computation that we're going to be doing later on. So Librosa again takes care of this resampling function. And if we run this, we'll see that because our sampling rate has been reduced by half, the number of samples we have in our signal has been reduced by half. After we've done our normalization, our trimming, and our resampling, we're going to transform our waveform. Note that our waveform is amplitude over time. What we really want is frequency over time. To do that, we need to compute something called a spectrogram. And Librosa takes care of this for us, but let's talk about is a spectrogram computed. So if we go here, MATLAB has a very nice summary of something called a short time Fourier transform. And this STFT is essentially it's taking a window of the waveform and decomposing the waveform into different frequencies to get our spectrogram. So we have this window of some length, and whenever we go to Librosa and compute the spectrogram, we can actually set how many points we want this window to be and how long is our window. The other thing is the hop length. So hop length is how is the window moving across the waveform. Let's say that it starts here. If it has a hop length of 2, maybe the next position it will be is here and then here. So it skipped some of the sections of the amplitude peaks, or effectively reduce or compress our audio signal. So if we run this, let's see what it looks like. We'll see that it looks a lot different. And y-axis, we have our frequency in hertz. And then we have the time of the audio signal as before. And then these brightnesses is a color map now, are corresponding to the intensity of the frequency in decibels. Let's print this so we can see our spectrogram. Let's see what the shape is. See that we get 40 in the x-axis and our time domain is about 1,000. So that's just how many time steps are here. But this is the number of features that we extracted from the audio signal. This is still a little bit much. So we're going to compute something called Mel frequency ceptural coefficients. And essentially that does is it reduces this using something called discrete cosine transform. So you can read all about it here, the implementation. We'll go to this example here. We'll see that this image is quite clear, and once you apply discrete cosine transform, you get kind of a blurrier image, but you still can make out the essential features of the image. So that's what we're going to do here with our spectrogram. Instead of having 40 features, we want to capture 13 features. This is just based on experience in the natural language processing field. So once we do that, we'll see that we get a compressed representation of our spectrogram. Our transcript data is all in characters, and we just can't feed in characters into our speech recognition model. So what we need to do is something called tokenization. So tokenization is converting the characters into integers that we feed into the model. Since we're working with Amharic, what we want to do is we want to identify what are all of the Amharic characters. So we'll go to this link over here. This is something called a Unicode chart. So this Unicode chart has international language standards for different languages. You have Hebrew, Arabic, but we want to look at Ethiopic. So these are the different Amharic characters. And you'll see that this is called Unicode, and this is the character appearance. So if we go back here, we want to loop through these specific Ethiopic character blocks. So it goes from 0x1200, so that's the beginning, and it'll span or span to 137x. So essentially, all we're doing here is creating an empty list, and we're going from the beginning of the Unicode characters for Amharic to the end, and for each Unicode, we are converting that data point into a character format. And then if this character has Ethiopic syllable in the name, so unicode.data is returning this string, and we want to make sure that it is an Ethiopic syllable. So we're making sure that it has this in its name, and we'll then append this character to the list. So if you run this, what do our characters look like? We'll see that we have all of our marked characters here. Next thing we're going to do is create a map of our characters to numbers. So we'll start this dictionary. So dictionaries have keys and values. Our keys will be our characters, and the values will be the integers that they correspond to. So we'll start by identifying the blank space to be value of 0, and then this special space character will be number 1. And then we'll start at index number 2 and go through all of our characters and add. So this character will be 2, this will be 3, this will be 4, so on. And then we'll add that to our character map. And we'll do the same thing with the index map. In this case, it'll just be a reverse representation. So our key will be the integer and the value will be the character. So if we run this and we print, what does our character map look like? We see that we have effectively mapped our characters to integers. And if we see what does our index map look like, it's the same thing but just reversed. So with this map, we can create our tokenizing functions. So here we're passing some text as an argument, and if this text has a space anywhere, we'll map that to our special space character. Otherwise, we will run the character in the text through the character mapping and append that to an integer sequence. So at the end of the day, we'll have a list of integers corresponding to the characters that we pass through the text. Our decoder, so this is decoding the integers into the characters. This will take in our integer list and pass it through our index map to decode what are the characters. So if you run this, we're going to do some tests over here. We're going to take the transcript from that audio file we looked at earlier, and we're going to encode that using our text to sequence. So that's our encoding tokenizer. And then we're going to decode that using the function. And we're just going to replace any of these space tokens with the actual space. And we're going to join everything together, concatenated. So we'll see here, if we run that, our original transcript is encoded into a list of integers. And when we run it through our decoder function, we get exactly what our original string was. Moving on, what we're going to do is create a data set that our model can use. So we're going to be inheriting a class from Torch's data set. So what that requires us to do is pass in our data frame path value. So that is the audio file path and our transcripts. And then we're just going to do the same pre-processing that we did before. So first we're going to load in our data into a waveform. Then we're going to normalize it using our z-score normalization. And then we're going to trim the audio samples. Then we're going to resample it, reduce the number of data points by half. Then we're going to compute our spectrogram. So converting from amplitude space to frequency space. We need to take the log. This is just for I didn't discuss this earlier, but our Labrosa feature MFCC. So if I search that up here, you'll see that the argument S, whatever we pass into our MFCC, needs to be the log of our MEL spectrogram. So that's why we're taking the log here. And finally, we can compute our MFCC. And this dot t is just called a transpose. So that is switching the dimensions. So at first it would be 13 and then the number of time steps. But when we do this transpose function, just switching the y and x dimensions. So now we get time steps in the x dimension and then the number of features. So that's 13 in the y dimension. What we do is tokenize our transcripts. So we create a label which integer representation of our transcripts, and then we return all of these values from our data set. So we return the MFCC, the tokenized label, the length of our MFCC. So that's just the number of time steps that are in our MFCC, and then the length of our label. Let's run that. An interesting thing about our data is that the segmentation of the time clips are different times. So you might have one clip that's 3 seconds, another clip that's 10 seconds, or another one that's 5 seconds. And when we're computing things in our model, we don't want it to have to adjust the number of samples it is processing at runtime. That's going to be quite expensive for our model. So what we want to do is pad all of the samples in the batch to the longest sequence. So what we're going to do is we're going to create a list of all of our MFCCs and a list of all of our labels in a batch. So what is a batch? So batches, we're sending our samples to the model in batches. So you might have a batch of length 16. So we're going to append all of our MFCCs within the batch and do the same for the other features that we're returning from the dataset. And then we're going to do this padding sequence. So pad sequence from Torch, essentially what it does is it takes in the features from our dataset in the batch and it identifies the length of the longest sample in the batch and pads the rest of the sample such that all of the lengths are equal to that maximum length with zeros. That's what this function does, and you can read more about that padding function here. So once we've done that padding, we can begin to talk about our ML architecture. Our speech recognition model is modeled after this foundational model called Deep Speech 2. And what this model is doing is taking the spectrogram. So that's what we computed. Actually, we computed a reduced representation of our spectrogram. And it's doing some convolution operation. So what is a convolution? If we go over here, there's a very nice animation that describes this. A convolution is essentially looking at the signal through a filter and taking the sums of the neighbors and reducing that representation here. If we go back here, we'll see that Torch takes care of this nicely for us. All we need to define is the number of our input dimensions, our output dimensions. This kernel size is the length of that window that was parsing through the signal. And the stride is similar to the hopping length, which we talked about before, but it's how many steps does our filter go through the signal. So if it starts here and then skips to this signal, that would be a stride of 2. Right now, this filter has a stride of 1. Once we've done that convolution, the next step in the deep speech architecture is these recurrent neural networks. So these are called gated recurrent units. So what's that? This is a variable that might help us understand what's going on here. So a gated recurrent unit is essentially 2 gates. One is the update gate, and that is deciding how much of our past information in the sequence do we keep. And the reset gate is determining what parts of the past should be ignored. And these are working together to update a hidden gate, which is the output of this recurrent unit. And bidirectional means that our sequence is passed both forwards and backwards, so it can retain spatial and time-dependent awareness. PyTorch is reducing the abstraction from implementing this. You just simply call this, and you just have to define this input dimension, the hidden size. So what is the dimension of our hidden gate? And then we want this to be bidirectional. In between our convolutional layers, we have these 3 things that we're doing. The first is this activation function. So whenever we are using our neural networks, we have these activation functions, and they're summing the weights from each of these nodes. The activation function is introduce nonlinearity into the model. This dropout is turning off about a fraction of the nodes in the neural network. The last thing that we're going to do is to fully connected layer. This is taken care of by PyTorch. This is a fully connected layer. And after that dense network, we'll have this softmax operation. What softmax is doing is returning a vector with all the possible characters, and those are each of the possible characters are represented with some probability. Actually, the logarithm of the probability from 0 to 1, and the most likely character will be selected. So once we've defined all that, the model architecture, we can run this. We get a very nice summary of the model. It looks quite large, but it's a lot of repeating units here. Remember that we have several of these gated recurrent units, followed by a linear and softmax. So once that's done, we have this data set that we defined from earlier that takes in our data frame, and we pass it through this PyTorch data loader function, which compiles all of our data such that it's able to flow easily into our model. And here we are initializing some things so that we can save the best model. So we have this timestamp and summary writer, and we want to use our CUDA cores and our NVIDIA GPUs provided by Google Colab, and then we can initialize the model to this CUDA device. This optimizer is how is the model backpropagating. So how is it updating the weights in the nodes of the neural network? CTC loss is a very nice paper that talks about this. Once we predict the likely characters within a time step, we will be left with something that looks like this. And this, of course, is not what we're trying to say. The model just assumes that at each time step there is a certain character associated with it. But we want to condense this. We want to collapse it into its readable form. So I could say cats and C's will be extended, A's will be extended, and T will only have one. But you would know that I'm saying cat. CTC is collapsing our predictions into the likely word. So if we go here, we see that there are several different predictions. All right, so once we've created these data, train and test loaders, we can begin defining our training and testing loops. So we're just take batches from the train loader, and we're sending these to the device. Our inputs are, so this is our features, our targets, which is our transcriptions, and then our input and target lengths. And note that we are computing our target length after it's gone through the model. Let's look at why that is. Go to conv1d. We'll see that after it goes through this conv1d layer, the output dimension is different from the input dimension according to this formula. So if you have some kernel size and some stride, which we did, remember we had a stride of 2 and kernel size of 11 here. Once you identify the kernel size and the stride, you can plug it into that formula and you can identify what is the input length after it's gone through the model. And of course, our target length will not change after going through the model. And we set our optimizer with 0 gradients. So every time the models run and it's updating our weights, we want to set it to 0 gradients before going through this step. We want to extract the outputs from our model given the MFCCs. And then here, note that the output shape is the batch size, the number of time steps, and the number of classes. And actually, what we want for the CTC loss is it to be in this form. We want the time to be first, and then the batch size, and then the number of classes. So we can do that using this permute function, which essentially rearranges the dimensions of our array. So next we can compute the loss function using our CTC. So it takes in the outputs from the model, the target transcription, and then the input lengths and the target lengths. And then we do our backward propagation, so updating our model parameters, and then we can step our optimizer so that we can tuning in the right direction. Then we can update our loss with the loss that we just computed. Every step we're going to be logging our batch loss. Every 100 batches, we're logging our loss function. So now for our valid loop. So an epoch is passing all the data through the model one time. We have several epochs that were parsed through. So first we will track our gradients by turning our model to training mode. Then we'll compute our loss function from training it through one epoch, and then we have our testing loop. So this is the same process as a training loop. We are taking in our inputs, we're permuting it, and then our targets, our input lanes, our target lanes, passing it through our model, and then computing our CCC loss. The thing different here is that we are setting it to evaluation mode so that we disable the dropout and normalization. So to track which model has the best performance, what we're going to do is look at the validation loss. And if our validation loss of the current model is less, so we have a better model than the previous one, then we'll save the state of this model as a checkpoint. So you see here a checkpoint. This is the best model from training. If you run this will take a lot of time actually, or take about 3 hours to train completely until you get loss values that start stabilizing. So if you run that, then you get this checkpoint with the best model. If you download it, you'll see it's about 365 megabytes, which is quite large, and we'll discuss that about how to deal with that later. We want to see how does our loss value change over running all of our data through the model several times. We change these. So I ran the model previously, and I just uploaded these to the Google Colab. Then I should be able to track how do the loss functions change over time. So you see that there's a steep increase after the first few epochs. Then as the training loss continues to decrease, the validation loss really doesn't decrease too much, and finishes around 20, 23 epochs. So let's see, what does our model predict given new data? We'll install this package called Jur, and we'll discuss why we need to later. And then we'll load our best model. So that's our checkpoint. And then we'll initialize what does our model look like. And then upload or update our model such that it is using the best weights and the best optimizer from our checkpoint. So we'll set our model to evaluation mode. So we're just running our predictions. We're not training right now. We'll take our inputs, our outputs, everything as before. And then the thing that changes is that the output of our models, we're actually going to take the exponent of that. Because remember we said the model returns the log of our probabilities. So when we take the exponent, we're getting the absolute value of our probabilities from something from 0 to 1. And then we'll take our prediction indices to be the maximum value of that vector of probability values. And we have something called greedy decoding. Actually, this is not the optimal way to do decoding. That would be beam search with a language model. But this is something that's very cheap to run, and it gives decent results. So what we're going to do is we're going to initialize an empty list, and for looping through the number of predicted indices that we printed here, we're going to see, is that label equal to 0, or is it equal to the previous character? And if not, then we'll append our decoded batch into the list. If not, then we're skipping. That's kind of what we're doing. That's what we're doing here. So we're just seeing, is this letter equal to this one? Yes, so we're going to discard that. The same thing here, and the same thing here. And there's nothing after this, so we won't append anything here. And we're left with a condensed representation of our predicted indices. So if we run this, let's see what happens. The last thing that we're going to do is we're going to print our true text and our predicted text, and we're going to compute something called a CER, or character error rate. And this is taking the characters of the actual text and the predicted text and just subtracting how many characters does our decoder get wrong. So that will be in a percentage form. When we're defining this model, we set certain output dimensions, certain kernel sizes, certain strides within our GRUs and our convolution layers. You can actually tune these hyperparameters using some advanced optimization schemes, and that you can use that to tune the model to perform better. The other thing is that this deep speech 2 model is pre-transformer. So transformer architecture has been widely used in the machine learning field. So now currently the state of the art, this is the current state of the art for speech processing. And what they're doing is using a transformer instead of our recurrent neural network, and it's just taking in the raw waveform, outputting the text. And the last thing is that the model is very large. Actually, the model size is 365 megabytes, and earlier I said that there's a way to reduce this size, and that's something called quantization. So instead of representing everything in floating point 32 or 64, you can represent them in integer 8 or floating point 16 representation, and that can reduce the size by several order of magnitudes of 2. And we'll talk about this in a future video. The other thing is that everything in here lives in a Jupyter notebook. How would you be able to deploy this speech application in practice? That's something we'll also talk about in a future video. To summarize everything we've done, looked at what are the basics of audio pre-processing. We looked at extracting waveforms, normalizing audio signals. How do we trim signals such that we only get whenever the speaker is speaking? How do we compute spectrograms, converting from amplitude to frequency space? And then looking at condensed forms of spectrogram representations. We also looked at tokenization. So how do we turn our string of characters into a list of integers? And how can we decode that back into integers? Looked at some at the deep speech to architecture, looking at how do we at convolutional layers, our GRU layers, several GRU layers, condensing everything with dense and softmax operations.
We also looked at how to compile data into effective forms for the model, setting up training as well as testing loops for the model, and analyzing how does the model performance increase over time, looking at things like loss curves over the number of epochs, and then decoding predictions from the model using techniques like greedy decoding to evaluate ultimately how well does the model translate a given piece of text using something called the character error rate. That's it for this video. As hinted, the next video will be about deploying the speech recognition app into production. If you want to keep updated, if you enjoyed the video, to like and subscribe. Thanks for watching, and I'll see you in the next one.